Let me introduce the panelists first. We have a pretty distinguished panel. We have Sujit Sharan, John Park, Amy Lujan, Thomas Stowe, Devendra Das Sharma, Steve Grutias, Deepak Kulkarni, and Mark Swinnon. You have heard them in the last couple of days. This is your chance to deep dive. I will kick this off with two basic questions. The first question is to everybody in the panel who would like to have an opinion on this. In the next 2 years, do you believe that there will be any companies selling IP in the hard chiplet form beyond memory stacks? If yes, can you point out to the data points? If no, why not? And what in your minds is needed to make this happen?
Well, there's clearly a chicken and egg problem, right? Who's going to make chiplets unless there's a market for it, but who's going to design them unless there's chiplets available? So I think that's one of the first challenges we face there, especially since most of the chiplet efforts have been vertically integrated in-house designs, such as the AMD one we just saw, where they design all the chiplets and all the substrate, and that's been successful. But commercial market, there's a question of how's it going to be started up. It's the ramp up.
Maybe I should ask Devendra then. Yeah. Now that the standard is out and there is, I believe, convergence around the standard, or at least broad interest, can you comment on the pace at which the standard will be adopted for it to become?
Right. So I think I would like to. So part of the standard is it's no longer, well, you can do a vertical integration play, but at least it levels the playing field for getting components from different suppliers, right? So yes, I very much would expect to see people selling chiplets, right? And that's the whole vision of Ucie, is that you can get dies from anywhere and package them anywhere, right? So in other words, I can get some dies from company X, some from their competitor company X dash, and then I can get other dies from Y and Z, and then put them in a different packaging house where they can package it together. It is similar to the way we as a broader industry, right? In this context, the we means the broader industry do anything like a system design today, right? You can get your CPUs from whichever CPU vendor you want. You can get memory from whoever you want. You can get accelerators and NICs from wherever you want, and they're all just going to play together because that's the way that ecosystem has evolved. So that's the vision of that ecosystem. Now let me answer the question about 2 years, right? Is it 1 year, 2 year, 3 year? Fine. I mean, it's in the near term future. Let me give a comparable example with CXL, right? So 2019, we did announce CXL, March, same time frame as this is 2022, right? And, if you look into the time frame now, and CXL is an open ecosystem, you have CPUs that are there, FPGAs that are there. A lot of people are demonstrating interop with CXL. So, how long did it take? It took a good 2 years or something for platforms to come up. But even before that, people were demonstrating interop, because generally your validation cycles are going to be 1.5 years to 2 years, right, before products really start getting out. It doesn't take once standardization is there, once people know that their investments are going to be protected, right? And once they know that there is momentum behind it, they put a lot of R&D into it, and it's very easy to get over the finish line at that point. And then it becomes a question of how long does it take for your part to be qualified and all of that. So yes, I do expect to see that, Ravi. 2 years or something. My crystal ball is not that clear, but somewhere in that ballpark. Yeah.
Let me quickly correct an error I made. Li Hong, my apologies, I did not introduce you. Li Hong is also part of this distinguished panel. Let me now.
He's my partner in crime in Ucie.
Let me now turn this a little bit to two different people in this. Amy, from your perspective, do your cost models accommodate for volume as well as yield capability when we do these sorts of analysis? You're on mute, Amy.
So I unmuted myself on my phone, but not on Zoom. So that's the second time I've done that. So yeah, as a starting point, we first try to look at cost from a high volume perspective, because we always like to know where is this product going to get. We always start a little bit best case scenario. But volume and yield absolutely factor in. Volume can be a little bit trickier because once you start talking volumes, you're talking price, not cost, and people are going to price things differently. But it's, yield is easier. It's more of a mathematical thing that you can factor in. And it's absolutely a chicken and egg scenario. Prices are going to be high until somebody starts adopting it. It's hard to adopt it when the prices are high. It'll happen. We saw this with interposers 8 or 9 years ago, I guess. We were standing around talking about interposers are going to be great to enable new technologies. Nobody wants to do it because they're expensive. Not going to get less expensive if somebody does it. So that chicken and egg situation is going to make it happen more slowly than I think everybody wants. But from a cost perspective, and we can get there if the yields are good enough. Chiplets are going to make sense. We've got to get there first. So it'll be a process, but it should pay off in the long run for early adopters. I think that they'll get to the cost benefit faster if you can weather the introduction.
Let me switch the questions a little bit and talk to our AMD colleagues and then move this on to John. From your folks' perspective, from the AMD perspective, for instance, or as users of standards of this nature, how do you see the evolution of standards from proprietary customized links to standardized links, which have a reasonable amount of capability? As you saw, Devendra showed a lot of capability. Mm-hmm. And then to folks like John, how do you make sure that this is ready as soon as people turn it? How do we make sure people can design on a dime, if you will? Maybe a question to Mark also. Okay, how can you design it so that the quality or the performance is guaranteed? So we'll start with maybe Deepak and Thomas and then move to John and Mark.
Deepak, you want to address first? I'll follow. Go ahead,
Sure.
Deepak.
Yeah, so I think the reason why AMD is part of this consortium is because we really do see the benefit of this standardized interface. And so we see the value of Ucie. And especially for a fabless company like AMD, we do want to have the ability to source from multiple different foundries, multiple different OSATs, to be able to package these things. Mm-hmm. So I think you will see as things progress, more products come out, AMD products come out with Ucie as the chosen interface.
Yeah, and I'll add on a couple of comments from based on Deepak's comment. Open standard is important because if you don't open the standard, well, the third party won't be able to participate. In these days, in this industry, we no longer do it alone, like in a vertical sense. Well, we have to have the support and also the ecosystem. Take examples of like in memory land, we have JEDEC, right? So it takes us, over there, it takes a couple of years or maybe more than a couple of years to understand like the brancher was talking about the KPI, right? The key parameter indicators. This indicator is not static, it's dynamics. As we go along, well, sometimes we learn about humbly that, oh, this KPI is good enough or maybe significant enough. And also, as we scale in terms of different technologies, well, our third-party ecosystem will come and say, look, well, this is good, but it's unachievable. It's all maybe costly. So the consortium with an open standard help us to learn together. At the end of the day, we are not enabling a company. We're enabling our customer. We want to provide the industry the feature set that makes sense to everybody. So.
John, you have a view of how you folks will be able to enable this?
Yeah, as it's been mentioned a couple times, but when we move to this world of multiple chiplets, 3D HI, it becomes very similar to a small PCB where we need tools like signal integrity to validate in this case, Ucie. And those tools are already in place. Cadence actually co-presented with Intel at DesignCon a couple weeks ago, specifically talking about our compliance kit for Ucie. And what that is we certainly have the tools to do the electrical modeling of the interface, but the compliant kit just automates the process by providing masks and interconnect models and those types of things. So it's leveraging the PCB technologies that have been out in the industry for a couple decades now. So I think from an EDA tool perspective, we're ready both to sign off on the interface as well as pre-plan it with pre-place and route, drop down some driver receiver models and parametric interconnect models and simulate that behavior. So I think in my view, the tools are in place.
I'll ask Mark from his perspective, and then I'll switch over to Lee Hong and Sujit, who are in a way users of this technology, to see how they look at life. Is it ready, not ready? Just to keep the conversation going. So Mark, go ahead.
Yes, I agree with John that the basic technology and solvers are available and have been for years, in the sense that package design have tools, PCB design to have tools, chip designers have tools and all that. The problem is that it's the world's colliding. It's being smushed together into one co-simulation problem. And Deepak mentioned that very early on you have to do an analysis across multiple parameters to see how you even start partitioning this design optimally, which means that you have to take in not just size and cost, but also like thermal, right? You don't want to put two hot chips right on top of each other. So you need to know that right off the bat before you even got, maybe at the RTL level, have to have some idea of the temperature. And then the other parts are, the electromagnetic interference. One of the reasons, and maybe, the UCI spec can talk to this, why the reach of the advanced package is only 2 millimeters, right? It's power, but also electromagnetics. So these come into the picture, and then there's all the mechanical warping and twisting of the multiple differentially thermal expansion parts of this. So all of these physics, which exist and have been, as John mentioned, PCB board have done this for years, but they're all being pulled together into a chip design environment. So I think that the challenge is partially tools. I mean, you need to have like 3D floor planning, which is only now coming on with the latest tools. You see Synopsys' 3D IC compiler, for example, is designed specifically to address that sort of challenge. But from the analysis point of view, it is more pulling these things together into a team that can and get the do you have the expertise? Often companies may not have the expertise because they outsource it, or if they do, one group is in Israel, the other group is in Bangalore, the third group is in Malaysia, and yet now they have to come together and work on the chip right off the bat together with all this expertise. And that is more the challenge, is how this multi-physics, what was before a multiple physics problem, becomes a multi-physics problem, where everything has to be considered together. And so the basic tools and solvers exist, but the methodologies are not in place. I think neither organizationally within the companies, except for large, vertically integrated companies like AMD and Intel that have that benefit. But for the mainstream market, where they're not as vertically integrated, how do you pull this expertise into a single group? EDA has a role to play there, in the sense that it needs to encapsulate a lot of this expertise in ways that makes it a lot easier for people to use. So it's not only bringing things together, all these physics, but also it's a much wider range, right? So suddenly chip designers have to look at thermal, have to look at mechanical, have to look at, for thermal, they need to know, well, what is the heat sink cooling? Oh, computational fluid dynamics for my airflow of my heat sink. I have to do that as well. It all becomes complicated. So the fundamental, as John said, the fundamental tools are there, but the methodologies of putting this together into a unified flow are not necessarily very mature.
So we need Renaissance engineers.
Yes, and that is sort of how much expertise are you realistically expecting from your designers, right?
Exactly. Yeah. So there's a training aspect, there's a tool aspect, and a collaboration aspect across geographies, across disciplines. Absolutely. That's great. And Lee Hong?
Yes, definitely, and that's why we are one of the promoters. I think I want to say the two key points. And the first, because we are as OSAT, as a manufacturing, so we kind of bridge the IDMs and also the system integrators. And in my yesterday presentation, we really want to collaborate with the bring up the ecosystem, but the standardization is very critical. We have thousands of customers. And if everyone provides their own platform, So that is not really easy for the manufacturing like us. So this is the one point I think I want to say that is very helpful and also very useful. So the second point I want to bring up is, as a manufacturing, we also provide advanced packaging integration. So we are kind of in the middle, and without the advanced packaging, how to integrate the chiplets together, that is impossible, to make the product. So from this point of view, like Devendra already said, this one is related, for example, bond pitch, and whenever technology want to choose 2.5D and organic interpowder, fan out, that is can provide the the standardization, the guideline, bond pitch, and also the routing density. So I think this is the 2 points from our OSI's or from our OSI's perspective. We think that standardization is very helpful, is very important. Yeah.
Yeah. So pointing towards standards, awesome. Would anyone else like to comment?
So just to follow up on that,
Yeah.
Since I come from the package design side of things, it is very interesting for us is that as package designers, we are now moving more and more into this space where we really have to interact very closely with the silicon design teams, especially for the back-end metal stack and the pitch bump layers, to make sure that we have the standards comprehended such that the package design also comprehends the standardization and is a very standard process in getting all of the different chiplets attached to each other. In the way that Devendra was showing the Ucie, it essentially is going to become more of a package play. You have put it on the silicon, you have right design rules on the silicon, but you need to be able to make sure that you have the right package architectures defined, the right package design methodologies in place, because in the past, we were all fairly worked in our own compartments and did not have that much interaction with each other. But once we start the integration of the chiplets, the package designers have to pick up a lot of the verbiage, the lingo, the tools from the silicon side of things, and vice versa, where we look at it as a whole, as a holistic piece, not just the package, but also with the board package and silicon. Because for us, we are the guys who interface between both the silicon and the board through the bump map and through the ball map. And anything that is done on either end of it affects the entire performance of the system. So from that perspective, I think as a package design team, we do feel this is very interesting, very challenging, but I think we have to work very closely with the silicon design teams and the EDA vendors. I think it is important to have a standardized methodology for design. It is very important to have the right tools for the design, and I think and to a certain extent, because there are different EDA vendors, we need to have a very good CAD agnostic way of transferring data across the different domains.
Right. So no more over the wall, right? It's got to be a hand-in-hand solution. Yeah, absolutely. So to that point, what do people feel is the maturity of the EDA tool change that are out there today? Are we just getting started? Are there some pretty major gaps where we have lots of human glue? What are people thinking in this area? And what are the kind of the key areas for improvement moving forward?
Well, from the EDA perspective, I think as mentioned, the actual core solvers are available there. You can do thermal, you can do mechanical, you can do electromagnetic, you can do chip power and all that. Those are available. There's two issues that come. One is capacity, right? So one of the problems with one of the challenges with these 2D, 2.5D, and 3D is that they're huge, right? And some analyses are simply additive. Some can be handled through reduced order modeling, but some need to be like electromagnetics. You really need to see most of the detail from top to bottom. So there's a question of do you see full system but not all the details, or do you see all the details but not full system, right? But full system and full details is starting to get very challenging. Now you can extend that, of course, and the cloud is essential for doing that, because we're talking hundreds of CPU hours and high-end machines to crunch through this. So that's one side. But the other side is, apart from capacity, is really platforms. You're looking at a huge range of tools, right? From packaging tools, chip tools, PCB tools, SI tools, the whole thing. And how do these tools work together? Traditionally in EDA, there's been a certain tendency towards the closed garden sort of approach, like mine, all mine, and no other tools can work together. And that's not going to work with this, exploding required number of physics and tools and analyses that all have to work together. So certainly at ANSYS, we've been working strongly at providing open and extensible platforms that multiple tools can work together on, can exchange data, where you can do co-analyses with data from various tools that have to be integrated to analyze what's going on. So platforms, I think, are the area where it's not so much the detailed solver tools that's the problem, it's more the platforms that allow the flow.
Got it.
Yeah, and I'll make a couple comments. So, yeah, the way things are set up now is there's a layout, substrate layout person, and then there's a characterization engineer, signal integrity engineer, and they're typically two different people, and it's quite a big loop to go from layout, get the geometries treated correctly so that they can be, like modeled,
simulated,
and so those flows are already in place to a large degree, where from the layout tool, you say move these geometries over to the EM tool, and they do their thing. Where the new improvements are coming are something we call Indesign Analysis. So while the substrate layout person's doing their layout, they'll get instantaneous feedback saying your impedance is off, or there's too much coupling for the signal. So I think that's where we're heading, is kind of more shifting left, so that sure, you'll still need to do sign off of the electricals, the thermals, everything of that. But ideally, the sign off is just verifying everything's good, not finding 100 things that need to go back to layout. So having that loop where we're moving more of the, all this electrical and thermal modeling up into the layout tool, I think is where that's an area that, for example, Cadence is investing in.
For more real-time feedback, yeah.
I'd like to take up on one point that Mark was making, and I think that's been a big challenge for us is interoperability across different EDA tools, because we are getting chiplet designs which are designed in different tools, and then we have our own package design tools, and we have pieces of different package designs coming in from different tool sets, and converting data across and making it valid across in our platform is our big issue. We have a lot of resources, and we're devoting a lot of time and resources to try to get to a more CAD agnostic way of doing things, so that we can export things from one CAD tool to another, read it in from one model to the other. Like you said, Mark was mentioning the closed garden approach is not going to work. We do feel that the EDA industry and the vendors will have to come together to define, like we have a Ucie standard, we probably have to have some common standards for all of these different EDA tools to be able to operate with each other, so that we can, irrespective of who is giving me a chiplet design and who is doing a piece of the package design, I can integrate everything together into my tool set fairly seamlessly. And that's where we have been spending a lot of our calories to get to that place. And I think it's more for the EDA tool vendors to also drive that.
Yeah, and I'm going to add on a couple of comments on that too. Definitely, establishing a usable or communicatable platform among different providers, a language or maybe parameters that are actually understandable and alignable. So that is important, because after all, vertically, where we still, I would say, breach it. Well, in terms of information or data exchange, by nature, Ucie, chiplet design will be tying or lumping the silicon design through the package design, as Sujit was mentioned earlier. How do we set up a common platform that we can communicate that give or take or trade-off among all these participants is important?
Yes, it's exactly right, and I think the open language is part of it, because an open platform needs to be extensible. It's obviously not going to solve everybody's problem without some customization. ANSYS's platforms, the ANSYS engineering design platform, ADT, and Seascape, are both have Python interfaces, and we actually have put PyAnsys, as we call it, out on the public domain on GitHub. So anybody can develop interfaces, develop scripts to read in and out of this ANSYS simulation environment, take the data in, take the data out, and all through Python. So we've Pythonized the entire system. And we see that as being, the world's most popular programming languages, the right scripting language, if you like, to make it extensible and open platform.
And there are some standards out there like IPC 2581 that allows you to move layout data into modeling tools. So moving, for example, from Cadence into ANSYS, there is a standard for that. It's not perfect, like no standards are perfect, but there is work being done in that space.
Yep, very good. All right, well, let's maybe take a question from the audience. First one, I think, is what is the test strategy for Ucie? And kind of switching gears a little bit to test and testability, which is actually my, I'm a manufacturing test guy, so this is my area. So yeah, maybe a question for Devendra.
Sure. So if you look at, so Ucie is an interconnect spec. So I'll talk to you about what are we doing on the interconnect side. Now, clearly there is going to be the test strategy for the rest of the chip functionality that everybody does, just like you do normally, whether you're doing integrating it on package or whether you are doing it as an off package connection, right? So from an interconnect point of view, we have things that define, for example, equivalent of loopback kind of stuff, right? So you can define, we have those. You have, when you put some things together, you can use basically the architecture defines well-architected configuration registers that will tell you where did you go through all the required link training steps, for example, right? That will be the first step. Did you see an error? When did you see the error, right? I mean, it lets you handle through those on a step-by-step manner. And then, as I said, you got the equivalent of the loopback. And of course, each and every one of the dies that are chiplets that you're getting, you need to make sure that they have their own equivalent strategy of making sure that that chip can be tested, right? And people do different things, right? So those will exist, but this has to coexist with that. Some of the other things that we also do is, in general, although the question didn't allude to it, that I always lose sleep over how am I going to debug this thing.
Yes.
That's right. So, and it's not an easy question, by the way, right? I mean, we have definitely done a lot of work, but I think this is one of the areas where we are going to evolve in a backward compatible manner, right? So like I was saying that, of course, it starts with us trying to figure out right from the beginning, did you go through step 1, step 2, step 3, step 4, and so on and so forth of the training phases, right? So we know exactly if something didn't work, where it didn't work, right? But then the question is, okay, hey, I was working everything was fine. Now something doesn't work, right? So then it gets into, okay, what protocols were you running? Where exactly did something not work out, right? I mean, all of those kind of things. So in general, what happens is a lot of people, each of us has got different debug hooks within the chips, right? So the question is that, can we make it in a way where you can expose your debug hooks? We have a sideband mechanism in Ucie. So can you expose those debug hooks through that sideband mechanism? And the answer is yes, right? But beyond that, it's very hard for a standard to say, hey, I just don't know what you are doing, right? It's just that, something after 10 hours, something failed, right? How are you going to go and debug? Well, this is the sideband hook. We provide you with a mechanism. You just say, oh, you go and read this set of RAM over there, and that gets you the right dumps, and then you can go from there. So,
right.
Yeah.
Anyone else like to comment on other interfaces, or the state of the state in terms of tool chains from a testability point of view? Like Devendra mentioned, having a common agreement across chiplet A to chiplet B is going to be very critical to ensuring that we can debug. And I would like to add, just my own commentary, that ensuring that we have a minimum viable DFT set, I think, will be an important part of any standard kind of moving forward. So we can assign, okay, who is at fault when we get a customer return, as an example, is going to be critically important. Above and beyond just, does the interface not work? Beyond. Yeah.
Actually, if I may add, to some of the things that I mentioned about all the configuration registers, we also have defined mechanism whereby you can margin the link.
Okay.
There's an architected mechanism to margin the link, so that gets you at least the electrical characteristics be covered. And then runtime, of course, we monitor the link health, and it gets reported and gets escalated, which is the escalation part of it is kind of free because you mapped it into PCI Excel. Because guess what? Those are, when you have hundreds of those lanes deployed in huge platforms, right? You need to have a mechanism whereby these things do get reported, and that's part of the benefit that we get. All that we have to do was map the these particular PHY into one of those mechanisms, and then off we go.
Right. Would anyone else like to comment as well on other interfaces that may be out there?
One quick comment from my side. I think we do need to acknowledge that the chiplet architecture in a way does move some of the testability burden over to final test, right? When you had this SOC, there was a lot of test content that you could enable at a wafer sort level. Now some of the die-to-die interconnect capability is tested only in a fully packaged solution. And so there are, in general, challenges that we need to acknowledge, that more of this testing will be done at a package level rather than at an individual die level.
And it's at a point in the flow, in the test flow, that's the most expensive point as well.
Yeah. I'll make a comment. So there is an IEEE standard for 3D stacks. To me, that's one of the biggest challenges when we go vertical. How do you probe a chiplet that's 4 levels up when there's nothing exposed? So, there's an IEEE standard. I forget the number, but it's all about putting in elevators to allow you to test from the bottom chiplet all the way up through the stack. So there
maybe 1838, I think.
Yeah, that's right. So that there's a standard there, and the tools are in place to support that.
Excellent. So one other question, maybe back to Devendra real quick. Would we assume that the co-packaged optics is also supported by your consortium?
So part of the UCI retimer that I briefly touched on is one of the usages would be co-packaged optics. And of course, that was the picture I was showing, if you remember, where, you would take things from your package level onto the, other trays or other chassis at the rack level or even at the pod level, and do the disaggregation that way, right? So yes, it's very much comprehended in the UCI spec. Of course, we define things on the UCI side. The optics part is its own optics part. But yes, absolutely, we define something. And the challenge there is, how do you make sure that once you do co-packaged optics, or if you have any other type of alternate media, right, through which you're escaping the package, right, that bandwidth doesn't necessarily match with the bandwidth that you have on the package, right? And we have solved that in the UCI interface. There are crediting mechanism and all of that specifically for the retimers that we have defined in the UCI spec to accomplish that. So it's reasonably thought out in terms of how we are going to go about it.
Okay, excellent. And Steve, would you like to comment?
Sure.
On your use.
As far as IR Labs, we see this as sort of first standard ever to include optics in chip-to-chip interconnects, and as Devendra actually said, doing even off-chip or off-package. So it enables maybe some more for doing something similar to flyover technology. That's usually on board technology down to a package level as well. So kudos to the overall UCI team.
Any particular challenges that you've seen or may see kind of moving forward in this area, Steve? Either in terms of standards or gaps in the standards that you really would love to have filled?
We're working through that right now, but we've studied the architecture possibilities, and we're seeing spin-offs, and also dealing with both disaggregated architectures and pooled architectures, which obviously both Deepak and Devendra alluded to. We just see this as just an enabling technology going forward. And, we're all for it because it enables a much better definition of future packaging.
Okay, excellent.
If I can add some color to that, Abram.
Go ahead. Yeah.
So just to add to what Steve was saying, right? The promise of disaggregation is this, right? In a data center, you got a lot of captive resources, and those are basically, and if you didn't know, let's say, today's model, if you look at it, right? I need to provision my memory for a reasonable worst case scenario. I need to provision my accelerators for a reasonable worst case scenario, right? And as a result, you have over provisioned everything, right?
Yep.
The promise of disaggregation is that you don't need to really over provision something. You will have some amount of resources that are close by that you're not going to share with anybody else. But then there could be these other resources that there can be, let's say, 10 terabytes of memory. I'll give you a specific example. Maybe in a rack, you're going to say, hey, I'm going to have 10 terabytes. Maybe somebody will say, I will have 100 terabytes. Let's not get hung up on the number, but let's say, some amount of terabytes of memory that is in the pool. I might have 10 accelerators in the pool, in the rack, okay, that anybody in my rack can use depending on their need. Now, when I can do that, I don't really need to over provision all of the servers in the rack. And the challenge with that model is that, how much of bandwidth do you get? And the promise of co-packaged optics is that you can transfer a lot of bandwidth with a lower latency, which is where you need this connection between Ucie and co-packaged optics. But then the usage model is really that disaggregation, where now you can not only do this disaggregation at a rack level, but you can even extend it to a pod level, right? Because then now what you're doing is that you're basically not having stranded resources anymore. Your resources are not going to waste. You're basically saying, hey, if I get a VM that needs an extra 5 terabytes, not a problem. I just go off onto the pool, get that 5 terabytes. If my VM needs an extra 10 accelerators, no problem. I can go off to the pool and get those 10 accelerators. And guess what? With the bandwidth densities that I showed you, you're not going to be hurting, right? I mean, it's a lot of bandwidth. And by the way, if you didn't need those, guess what? You turn those off because the power savings are pretty good too. So, that's basically the promise that we have, right? And of course, all of these will need, you're asking what are the barriers? A lot of software needs to be developed. We need to prove this out, right? I mean, all of those things, right? But those are all engineering, which we can all get over. I think we are building the infrastructure, both in terms of CXL, as well as now with Ucie to realize that vision.
Yep. Excellent. All right, switching gears a little bit. I'd like to talk about economics, test economics. So we had a great presentation earlier today with Deepak looking at solvers, machine learning solvers. Amy as well, a couple days ago, had a great presentation on, looking at yield trade-offs and things like that. But, just looking for my own work, I've seen had a lot of feedback, both internally as well as externally outside the company. From designers and architects saying, okay, this space is extremely complex. There are so many trade-offs that to be had, where the designers and architects are befuddled really at the PowerPoint level stage of the design process to really figure out what is the right partitioning, what are the right trade-offs, how does this impact test, how does this impact manufacturing. This is, hard for any one person to put their mind around at any one point in time. What's going on in the industry today? What are you doing today? Are people using more pervasively AI engines? Are people using Excel spreadsheets? Is it just human glue that's trying to solve these things? What's the state of the art today, and what's going on in this space? Who might like to start? Amy.
I was voluntold.
Okay.
So I don't have a very good answer because most of what I do is reactive. I work on the cost models that somebody has asked me to work on. I can tell you that no one has really said, I am ready to look at the cost of my chiplet design. I have one customer who is modeling multiple advanced technologies that do support chiplets. And so I think that's where they're going. But while cost is an important question, it's not quite the first question. When you're sitting down and you have all these, like you said, it's complex. You have all these things to think about. I want to build a chiplet design. You do have to figure out first what your chiplets are going to be, if they're available, And you do need to have some idea of which packaging technology is going to work. You know, when I talked about the cost of different technologies, 2.5D, standard on substrate, embedded pieces of silicon, yes, some of them were cheaper, but the cheaper ones might not support enough chiplets for you. So that's why it's never just about cost. Like, obviously, you want to do the simplest packaging technology, which appears to be fan-out on substrate. But if it doesn't support the 4 chiplets that you need, if it can only support 3, then it's not your answer. So, you know, the cost is not, it's one of the most important questions to ask, but it's not the first question to ask. Don't waste your time building a cost model for, check your chiplets in a packaging technology that's not ready to support enough RDLs for you. Right. So because it's not the first question, I don't think anyone's there yet. There's a little bit of exploring happening, but I'm not seeing a lot of, it's time to look at my costs. I think that people are still struggling to find the first part of the path before they get to that second part.
Yeah, maybe I can add a few comments over here. Sure. I think the way we are looking at this is, like Amy alluded to it, it's not cost as a standalone metric. It is definitely power, performance, area, cost, and in many cases also time to market, because that's one of the key advantages of chiplet, which is you can think up a new design and reconfigure a set of already validated chiplets to get a product to market. So when you're thinking of solvers or tools that enable this process, you do need to think about it holistically. How do I help with those trade-offs across all of those vectors? Right? Maybe the change in philosophy that is happening is it's not a discussion only within silicon designers anymore. Packaging engineers are right front and center all the way from concept. And so you do need a portion of this from a human glue to say, here's what I understand about the architecture and what it can provide along all of these vectors. The main advantage of the tools is in being able to quantify that, right? Instead of it being an abstract guideline saying, this is what 3D can provide, you are able to quantify and say, here's the benefit in terms of yield, or here's the benefit in terms of performance that 3D packaging can provide.
Right. Excellent.
Maybe I just follow up, all this topic from our side, and we feel more challenges both on the test and also the cost. So from test point of view, and since we are doing the advanced packaging, so we received the so-called non-good die, the chiplets, and after that we make it integrated on the if before is simple on the substrate. So for this flow, we call the Fluxy BGA is kind of very controlled very well. But since the advanced packaging, like people talk about here during the few days, and for example, 2.5D or fan out. So this one we have to make by ourselves. So how to test it? The interposer and 2.5D interposer, we have some standards. People can do test it. But how about the fan out? And the fan out and also fan out embedded. Those kind of tests is very, very critical. But currently, the best test we can do is just maybe very simple OS. But most of the time, we only do the virtual, like the optical inspection to make sure all this RDL manufacturing is good. But we still have the chances to lose, the non-good die when we put on the interposer, especially on the fan-out interposer. So this is the challenge we are facing right now. Even though we're working with some ADM companies, we comes out some test program, but still very limited. So regarding the cost, so this is also, when we add, Imee's cost model, and Ieee mentioned about that, how to we evaluate it, like us, like manufacturing cost loss. It's not only the manufacturing yield, and because we cannot do fully test and functional test before when we do a partially assembling. So that is a kind of also add the cost. And when you consider all this, the entire system level integration. So we feel a lot of challenge on the test, especially for very complicated platform for chiplets integration.
From that perspective, Ibrahim, actually, one of the points that she's making, which is KGD becomes a huge issue. I'm not even sure if on the chiplet basis, how are you defining a KGD? The problem for it becomes is if you are going to assemble a whole slew of chiplets on the package and you find out, and like someone mentioned at the end of it, that you at the package level test that I have a problem with one of the chiplets, it's a big deal. The problem, of course, with KGD is that it is still a subset of the test. And I'm not even sure on and maybe Devendra can comment on that, I think he did add this, how do you test the chiplet on the UCI interface when you don't have the other end connected? And then you have to get this whole thing into the package on the interposer, and that's where you start looking at a couple of other strategies, which would be, is there a rework strategy possible? Can I, at some point in my time, be able to test it, find out, hey, one of my chiplets is not working, can I rework it? Can I remove that, put in another good one back in there? So, and then partial assembly test, things of that nature have to be developed to be able to, at the end, because at the end you can't, it's like a small PCB now, you don't want to throw it away at the end. Right. So I think those are some of the real key challenges that we'll have to address.
Yeah. No, go ahead. Sorry.
So Abraham, back to the original question about how to navigate, the complexity of this this world. I think one of the key changes that's changing the industry driven by this is the greater involvement of foundries into this area. So we've seen foundries starting to suggest, rather than just a technology which you could make any sort of system you wanted, they're coming up with like 4 or 5 or 6 semi-pre-digested system, like a chip in the middle and 4 HBMs on the corners in this sort of package with this technology. It's sort of like they've pre-done some of the work and trying to make it easier for people to get in there and just say, here's option A, B, C, or D, pick one of those 5. And that system will seem to work, and we've done some analysis on it and give you guidance. So they try to reduce the degrees of freedom, and also that's to promote usage amongst the mainstream. But it also, and I think this is something that is sort of coming in through the back door a little bit, but the whole 3D IC system becoming more chip-like from the PCB side means also that the very strict formalism that is employed by foundries in sign-off and validation is bleeding into this world as well. Now suddenly package designers are faced with foundries saying, okay, have you run the proper tools? Have you run our DRM through this? Have you done the EM, the thermal analysis? It's exaggerating a little bit, but in PCB often was more like Jeff next door says it's okay, so let's go. While with foundries, it's very formalized, it's very streamlined and procedural, and that's coming to the 3D IC world as well. And they are also helping to people navigate the complexity, I think.
Which is a good thing. Yeah, helps simplify the road ahead. So I think on maybe a similar topic, I'm going to take another question from the audience here. So we talked a little bit about cost. We talked a little about kind of the landscape and what are some of the tools that are around that and kind of the focus areas. But how do we, early on in the process, how do we assess the chiplets quality and reliability moving, as it integrates and, before it integrates into the final design? Is there a way to sort of predetermine what this is so that we can predict, as an assembly house or an OSAT, what the final yield and reliability at the end of the day will be? You may be limited by the reliability of the least reliable component within your chiplet ensemble. Is there a way to communicate that and assess that and provide that from, let's say, a chiplets provider early in the process so that we have a highly manufacturable product at the end of the day?
Ibrahim, actually, I'd like to expand on that question. This is something that's been bothering me for for quite a while now, talking about 3D-IC in the back of my mind always, is that I'm old enough to remember when systems were much more disaggregated, and we were taught very early on, and it's still true today, that the connector failure is the main reason for system malfunction, right? That has always been true and is still true today. And I remember one of the huge benefits of going to monolithic designs was that the number of connections is drastically reduced. It's all in one system. And that was seen as a huge benefit, right? And we've sort of forgotten that a little bit now because we've been working with it so long. But now we're going back to a disaggregated system, which means the number of physical connections between electrical connections is exploding again on the board, right? And I'm always thinking that must be bad for reliability. I mean, everything I've always taught and all my experience says that is not good for reliability. So I'm just amplifying that question. So, we always talk about cost and how wonderful the possibilities are, but there's downsides as well. One of them, I think, I'm afraid, is reliability. And I just don't know enough about it. I'm curious about the opinions of the panel on that too.
Yeah, would anyone like to comment on that?
Sure, I can get started on that.
Go for it.
So if you look at, for example, let's talk about on-board kind of interconnects today, right? Pretty much all of them, you have very good way of testing them out, right? I mean, there are failures that happen because you have something on the design phase. Those are, of course, you have to debug and get those out. And then there are failures that that happen in the field, right? For the ones that happen in the field, you go through and, there are mechanisms like you're going to go through link width reduction and all of those kind of things, right? So not ideal, but at least you're not really completely off, right? So to speak. And you've got hot plug and all of those capabilities. Now, the things become interesting once you're on package, right? You can't really remove something. Once you're packaged it, it's packaged, right? Now, the question is, how do you deal with connections that are not there? And at least from a UCI perspective, for all the advanced packages, we have the notion of spare lanes that you can replace them dynamically, not just during the first time, but also let's say, a year or so from now, you powered on and the thing is not working. Some lanes are not working. That's fine, not a problem. You can go to the spare lanes and replace them. And for the standard package kind of option, we could have added spare lanes, but after a lot of discussions, I mean, that possibility is still there, but we said, hey, that should be similar to what you do today on PCIe or CXL, which is that, you just reduce the link width and operate at a lower link width, right? And then there are other things, right? If something gets marginal at higher data rates, you have the option of downshifting the speed. So we have deployed a bunch of these techniques, right? I think there is the other part, which is, let's say if you package a lot of memory or something, and those have inherently different failure rates over time, how do you deal with those, right? And those, I believe we have to deal with them through things like, better ECC, RAID, and all of that. And the industry is going to innovate, right? I mean, they're going to do all the analysis. We are going to do all the analysis. We're going to say, hey, these types of components, they have a failure rate that's higher. So what do we need to do? And there are well-known techniques that we can deploy. Of course, it's always going to be a cost and all of those trade-offs, right? But it's not like, you're powerless. It's like, we got a lot of tricks that we can deploy and make this thing as reliable as we want them to be.
Do people see the need for redundant chiplets? Entirely redundant
Whether
chiplets?
it is redundant or, I mean, it's not really, okay. So it's unlikely that an entire accelerator is not going to fail, okay? Because that number you do the analysis, which is known as the fit analysis, right? So the question is that, is the failure in time of a given package going to be, what's the number, right? You're going to come and compute that. And if that number, you're going to get a number. And, if that number is not acceptable, you're going to look for ways in which you can get around to those kind of issues, right? And, that it's the same thing that you have today, right? Say, if a core goes bad, well, you got n-1 of the other cores, right? You're going to still work around. People are going to come up with those kind of solutions that's going to let you move along, right? You're going to have some redundancy within each and every one of the chiplets if it doesn't meet the fit goals, so to speak. And here, of course, I'm going on a limb and trying to predict how these things is going to evolve. But, it's a reasonable way of proceeding forward, right? And then And then, then the question is, what about the reliability at the interconnect level? Well, those are all addressed, right? And then, in the question of, okay, hey, if you have memory and the whole thing fails, then of course, you're going to have, that's why you've got ECC on the, we have today, right? On the, you can deal with chip kill and those kind of things. So those type of technologies will be deployed there too, right? You will have RAID and all of those. So yes, redundancy, right? From that point of view, right?
That's right.
Maybe to build on the conversation here, I think what Mark was getting at is that inherently the number of interconnects is increasing. And if you look at the number of board interconnects that we have today, board level interconnects that we would have, they would be in the 1,000 to a 10,000 range. Whereas when we talk about die-to-die interconnects, especially in 3D type architectures, these are increasing sometimes to orders of magnitude higher. Right. So inherently, the number of interconnects and the possibility for one of these not to function well is higher. I think the redundancy component or the design upfront to be able to keep in mind manufacturability, yield, and reliability plays an important role. So we do need to keep those things in mind at the initial phase of these design. But also it means that there is a bigger onus on the packaging side to make sure that there is rigorous testing capability as well as reliability capabilities that are comprehended in here, right? So I think it does shift a little bit of that focus again from here is what I could design and test at an SoC die level and ensure that it would function well in a product to now the die-to-die interconnects become an important portion of the design phase as well as the reliability testing that needs to be done. And that's where, again, I think the choice of the packaging architecture it plays an important role. You need to make those trade-offs on what is the performance that you expect to get from this packaging architecture and how do you ensure it still meets the market segment needs on high reliabilities, high, life for these packages.
Excellent.
Yeah, but maybe I just add 2 coins and regarding also Deepak and talk about and also Mike asked. So from our point of view, I think we see how to make sure all this yield complexity of chiplet integration. So we found out first the development cycle time right now is become longer if we compare the simple package, type of solution. So the reason why, just like Deepak said, now also everyone asks because the design up front is very important. How to ensure the design feasibilities and also match the manufacturing abilities to make sure the high yield. So this we see the development, cycle time and is become longer. And secondly, we see the yield learning path for us also become longer. So start from the beginning, from the NPI, from the technology quad to NPI to manufacturing, all this yield learning, how to make sure all the chiplets integration on the field with a high yield and a less reliability risk. So that is we see the 2 longer cycle time. And on the manufacturing and on the yield learning path for us, it's become longer. So that is something, the key challenge we see here. Yeah.
Yeah. So the cycle time has grown. Yeah. Maybe on a related question then, also a question from the audience here. Who owns, maybe more from a business model perspective, who owns the losses at the module level at final test? If you see something coming in on maybe an immature carrier of some sort, and you're trying to integrate, is it the integrator's fault? Is it the chiplet provider's fault? Is it the fab house's fault? How do you determine where to place blame and how to fix the problem moving forward typically? Maybe a question for Li Hong might be a good way to start. How do you handle these issues, which I'm sure come up?
Yeah, I think that is a very good question, but a very complicated and not clear answer for this. Yeah. So So yeah, so definitely involve a lot of things. And for us, for example, we are kind of the old sides make the integrators, make the product. So if something happened, the first blame, maybe from our customer is us, right? Because we deal with a good product, supposed to, right? So yeah, so that is the things we always see this phenomenon. It's not straightforward. Then if we got something wrong, we have to debug either the good die, the incoming die issues, or is our manufacturing issues, or some kind of design, because design issues, for example, structure design issues, they've been resolved. Suppose at the beginning, that's why we said we have to collaborate with the designer up front. So after if we resolve this, the two really is material. Like for example, whether it's the upfront, the foundry, the chiplets issues, or our manufacturing issues, or potentially some design issue caused some reliability, but did not catch during manufacturing, during our reliability test, but it failed in the field due to the time. So that is something we have to figure it out, but not straightforward. Who will be in charge of this? It's very difficult, So
what do you? Okay, go ahead.
So I said manufacturers will be the first one to take this responsibility, but you have to analyze in details what's the cause, what's the root cause of the failure, and who really to get the.
Yeah, if you could create something magically by snapping your fingers right now that you don't have today, what would that be that would help your process of figuring out root cause and resolution of some of your key problems right now? What's missing right now?
So right now, that is kind of all basically business discussion. I can say that, so you have to discuss with the customers, set up the business model at the beginning. And if something lost, who will be in charge? What kind of percentage? So currently we see the solution is from business discussion. Yeah.
Okay.
Not from technical, perspective more. Yeah.
Yeah. So you think you may have most of the technical pieces already?
Yes.
To get what you need. Okay. Excellent. Let's see. So maybe staying on the business model side of the world for a little bit. So how do you see, or how does the group here see the business model for third-party chiplets kind of evolving over time? Right now we have a lot of IDMs that are kind of producing their own chiplets, right, in vertically oriented structures. We have 3D die stacks today, memory die stacks. Where do we see things going from there? What other hard IP blocks could be maybe next up beyond DRAM that may hit a quote unquote open marketplace? Where's the next step for chiplets?
Certainly a complicating factor in that is that we talk about bare die as if they're just the same as in the regular chip, just without a package or something, but that's not actually the case, right? If you target the chip at normal packaging, you have to have big, strong drivers and on the periphery to drive those big PCB lines. But if you're going to put it in a chiplet, you're going to have a completely different I/O protocol, different power and drive capability. So the chiplet design is unusable in anything but a chiplet. And the standard chip is not appropriate for a driver. So it's not like you can take an existing product and sell it at a different market. You have to redesign it for a chiplet and can only be sold to chiplet. So it is a very targeted market.
Right. Do we see sort of chiplets, from a marketplace point of view, being restricted to primarily IOs moving forward, and maybe the hard or sort of the secret sauce IP is kind of handled by specific IDMs or specific vendors, that kind of thing. Is that kind of how things may proceed moving forward?
I think,
Yeah.
so let me see if I can address that. So
go ahead.
If you look into, whether you're doing an accelerator or doing a smart NIC and things of that nature, right? Yes, today you do that with a PCI Express kind of a front end, whether it is PCI Express or CXL, doesn't matter, right? You take that one out and you plug in this, UCIe interface, and it's at that point, you're not, of course, talking on an external link, but you're on an MCP kind of a link, right? You will see that a lot of the companies that do, and by the way, it's a very thriving market, right? If you look into the CXL or PCIe marketplace, right? I mean, you got a multitude of companies that are doing their own set of things, right? And things that they're good at, right? So I can completely foresee that some of them are going to say, hey, maybe this part of mine doesn't consume as much of power and it adds a lot of value. And by the way, I get a lot of bandwidth and power efficiency and all of that. So I could do many more interesting things. My accelerator can be suddenly a lot more efficient if I integrate it on the package with the CPU, because guess what? I get access to the entire memory that the CPU is connected to. I get all of those, right? I get access to its caching hierarchy, and I can do, and I get to access that with a very low latency, right? So that enables me to do a lot more things that I was otherwise able to do sitting on an external link, right? Because my bandwidth density is a lot better and all of that. So that opens a lot of doors for those kind of folks, right? Things like accelerator, things like smart NICs, in addition to the memory and the IO kind of folks that you talked about. They are the ones that are going to come and make the offerings, and they're going to integrate their solutions into onto the package. And it's going to be I believe it's going to be a truly open field where people can really innovate. Because if you give people, that was the KPIs that I talked about, right? If you give people incredible amount of bandwidth density, very low power, right? Very low latency, that opens the door. And the right protocols, right? I mean, the caching protocol and the memory protocol semantics, and in addition to the IO semantics, you can do a lot of very interesting types of things that is going to change this landscape going forward.
Yeah. Would anyone else like to comment?
Yeah, I will. So Cadence, as an IP provider, we are providing chiplets, but it's not, we're a long ways away from that world of having like a PCB where you open a catalog and have hundreds of parts to choose from. That to me is really far off. But where we are today is we are developing with our partners chiplets. As Mark pointed out, you don't just take IP and convert it, snap your fingers and it's chiplet. You have to put a wrapper around it that handles test and works off of Ucie or whatever standard the customer might want. So I think as IP providers, we're already starting to work with some companies for their own internal use, right? They're not going to share that chiplet that we're code developing with them. And it's the business model is basically the NRE costs and then some sort of royalty on top of that. So right. I think that's where we are today. There are some people that are kind of mostly, I think, a lot in aerospace and defense that are providing more, off the shelf. I think of, Jariat, I think Ieee, I think they have. So we're moving there, but we're moving slowly to this world of, widely available chiplets. It's going to stay, kind of secret sauce internally at companies, whether they develop the chiplet themselves or work with an IP provider to develop that chiplet.
Thank you. All right, so nearing the end, I think, of the session here, but I'd like to ask one more question here. So as we look to the future integrators, the future designers moving forward, and all the universities and education systems that need to kind of provide this new talent, what would each of you say, I guess, are some of the key skill sets that are needed for this really new breed of integrators that are needed to both design chiplets, integrate chiplets, test chiplets, and get them into a product that's sellable? kind of moving forward. What are those? What is that skill set list, and that may or may not be in existence today that needs to be developed? Who would like to start?
Well, looking at the university education, I think it's and I've seen systems in various countries in Europe and America and all that, how they educate engineers. My opinion is that we should make sure engineers get a really broad and deep fundamental physics engineering education. Not so much about which part has to, it can work in this circuit or how to design this practical part, because that changes so quickly. It's really, they learn that on the job. But working out of university, having a fundamental understanding of how optics and fibers work, how electromagnetic fields interact, how thermal flow works, and all these basic physics, which are unchangeable and always there, and are becoming much more brought to the fore in these designs, right? And we had the luxury for a number of decades in digital design to get really abstracted from the physics, but it's all coming back to us now, and we need the education to be not so industry oriented, but more fundamentally understanding the physicals and engineering disciplines at a deeper level, so that you can apply them through your career as these effects become, crop up. So that's my sort of take on that.
Engineering fundamentals. Thank you. Who else would like to comment?
I can go next.
Yeah.
So I think
please.
I do agree with Mark that and fundamental understanding of some critical areas is important. I also feel that a exposure to the breadth of design, including understanding of thermal issues, electrical, mechanical, and knowing some of these trade-offs that you have to do in terms of a package design will be a good exposure. Maybe it is complemented with the fundamental experience with some internships or other industry engagements, but we need to look at this as not just a deep area of expertise, but also as a breadth.
Absolutely. I love the idea of internships, by the way. I did many myself. Who else would like to go?
Yeah, maybe I just, based on what Deepak and Mike and they covered, I just want to make one, just go more hands-on and the collaborations on get into the real world, and especially internship is very important. Yeah.
Excellent, thank you. Anyone else? All right, I think that takes us to the end of our panel discussion. I'd like to thank our presenters. This was an amazing discussion. I learned a lot myself, took a bunch of notes, and I hope you all enjoyed this and learned yourself some areas that are new and important for integrating this future of chiplets, which is upon us moving forward. So thanks again.
Thank you very much, Abram, and Ira for organizing this.
Thank you very much.
Thank you.
Yep, Ira, you're on mute.
Thank you, Abram. Thank you, Ravi, for moderating. And I want to thank all the panelists for your insights on the panel and all of your great presentations over the last 3 days. So thank you very much. And once again, I'd like to thank the sponsors who made this event possible, Advantest and ASC Group. Advantest having high customer satisfaction surveys for over the last 30 plus years from VLSI Research, and the highest ratings in the last 2 consecutive years. So congratulations to Advantest. And thank you to ASC. The chiplet era has begun, and as we've talked, heterogeneous integration will play a vital role in bringing chiplet-based designs to market, and they are working on the advanced packaging technology and working with everybody in the ecosystem to make it happen. The future is heterogeneous integration. And with that, I will thank everybody for joining us and look forward to seeing you at a future MEPTech event. Have a good rest of your day. Thank you.